Good morning, students. Today we are going to look into Schrödinger time dependent equation and Schrödinger time independent equation. These two equations are very important in quantum mechanics, and they are all base in quantum mechanics. And in fact, yesterday we looked into the wave function. The solution of Schrödinger time dependent equations will be the wave function. So main concept of Schrödinger equation, it depends on the concept of conservation of energy and de Broglie concept, de Broglie hypothesis. So these two things are very important to derive Schrödinger wave equation. One is conservation of energy, and of course we know conservation of energy is nothing but kinetic energy plus potential energy equal to total energy. So this is one idea. And second idea is de Broglie hypothesis, which is nothing but lambda equal to h by p. Yesterday in the last video we looked into clearly about the hypothesis, de Broglie hypothesis. For all the material particles are associated with the wave. So this was the hypothesis set by de Broglie, 1923-24. So he got Nobel Prize in the year 1927. And in fact, in the Viva examination for his PhD thesis, the professor asked him, can you do it experimentally? This is lambda equal to h by p. He derived out of these equations. And of course, E equal to h nu, we know E equal to h nu from Planck's idea. E equal to mc squared from Albert Einstein's idea. So he has taken these two equations and he derived lambda equal to h by p. So equating these two equations, that will give you h nu equal to mc square, nu equals c by lambda. So hc by lambda equal to mc square. So lambda photon can be calculated. C gets cancelled. You have h by mc. For any photon, this is mc. For any material particle, this will be mv. V is the velocity of the particle. C is the velocity of the light. Okay. So out of these two equations, he derived this equation lambda equal to h by p. So one of the professors asked him during the Viva examination, can you prove it experimentally? So at the time he said, in 1915, X-ray diffraction was very famous, and X-ray diffraction was very famous in the year 1915. So similarly, electron diffraction also can be done, he suggested. And in the year 1927, before that, because of Davis and Germer experiment, and this was proved. So lambda equal to h by p. So same year, in the year 1927, he got Nobel Prize. So Schrödinger took this concept of lambda equal to h by p. Okay. So 1923, de Broglie suggested that all material particles, all moving particles will have dual character. So it's a particle nature as well wave nature. In fact, lambda equal to h by p, p stands for mv, correct? P equals mv. Suppose if I am moving, surely I will be associated with the wave. So this is what it says. But myself, I am not prominent because it just take mass of weight of myself. So it will be around 50 to 60 kg, correct? So if you substitute here with the velocity, less velocity, with the mass, and of course h equals 6.63 in 10 power minus 34 joules seconds, correct? So what of lambda? Lambda will be very small. Suppose if I have an electron has the mass 9.1 10 power minus 31 kg. You substitute here and this will be exactly of the order. So that's why all small particles, quantum particles, will be prominent. They can be visible in the visible region. So the lambda is seen, lambda is known. For us, lambda is not known because of the weight. We are not prominent. Okay, because of the mass. Mass is very high, their mass is very less. So wave particle dualism represents a dual particle nature, and of course here h is nothing but Planck's constant. And each material particle behaves as a group of waves, and of course we said, yesterday we discussed, so this is the group of waves. Okay, at the antinodes. So you look at, this is a wave packet. Each wave represents a wave packet. Okay, in which we have superposition of lot of waves inside. Okay, superposition of material waves which are inside. So suppose if the particle is present at the antinodes, so they are all nodes, they are all antinodes. So particles present means it implies that the constructive interference takes place between superposition of all material waves which are inside. So this is the group velocity, this is the phase velocity. Group velocity is equal to particle velocity. Okay. So in terms of wave vector, we can write k vector equals p divided by h bar. So momentum of the particle can be represented in terms of h bar k. Okay, actually this is the eigenvalue of the momentum. So p equals h bar k. So when you are studying quantum mechanics, surely you should know about the eigenvalue of the momentum. So I have already said about one eigenvalue, which is nothing but p equal to h bar k, where k is the wave vector, which is nothing but the direction of the propagation of the wave. Yesterday we discussed about the k vector, correct? And how it has come? See, p equal to, we know that lambda equal to h by p from de Broglie hypothesis. So p equal to h bar k, k equal to 2 pi by lambda. Okay, so substitute in this equation, we have p equal to kh divided by 2 pi lambda. Okay, so h divided by 2 pi will give you h bar. So okay, so p equal to h bar k. Okay, is it okay? So Schrödinger to the concept of de Broglie hypothesis and the wave equation of the solid. So Schrödinger, he has taken, already told you, Schrödinger, he has taken, first idea is de Broglie concept, then another idea is conservation of energy. Okay, he has taken a solid, he has taken a wave equation. It so happened that Schrödinger from Austria, Vienna. So once he was a professor in the university, so he gave lectures. At the time, a professor asked him, "You are talking about always waves, waves, waves. What is the wave equation?" At the time, de Broglie was very, very famous. So Schrödinger took his idea and started giving some discussion in the seminar. He always said waves, waves, waves. Then immediately one professor, was Peter Debye, who got the Nobel Prize for chemistry. He asked him, "You are always saying about waves, waves. What is a wave equation?" That indulged him to find out the wave equation for the quantum mechanics, which is the base in quantum mechanics. So he took the wave equation of the sound wave equation in one dimension, which is given by this equation. So we have already studied this equation is a sound wave equation. Partial d squared psi by dx squared equal to 1 by v squared. V is the velocity of the sound, d squared psi by dt squared. So look at the left hand side, it depends on the x. Look at the right hand side, depends on t. And of course psi depends on both x and t. It is in one dimension. So it's very clear. So psi is a solution. So it's a linear equation, because the solution also will be linear. The transformation will be linear. Yesterday we discussed the linear property yesterday very well. So psi depends on x and t, where v is the velocity of the sound, psi is the displacement of the wave, which depends on. So he has taken from the sound wave equation. So in 3 dimension, this can be written as like this, equation 1.27. 3 dimension, we can write Laplace operator del squared psi, which depends on r comma t, d squared psi by dx squared plus d squared psi by dy squared plus d squared psi by dz squared, which is equal to 1 by v squared d squared psi, which depends on r comma t, divided by dt squared. Okay, now the solution. What is the solution? Solution will be psi. Correct? Solution will be psi. So the solution can be written, the solution can be assumed sin omega t or cos omega t, e power I omega t or e power minus I omega t. Any one of the solutions we can have, or the suitable combinations. We can combine these two, we can combine two, and that also will be the solution. So some of the linear combination of solutions, as I said just now, this is a linear differential equation. The solution also will be linear. So linear combination of the solutions. So we assume that wave amplitude at r is periodic in t. Of course we will not assume. Consider a solution of above equation as psi of r comma t, which is equal to psi of r e power minus I omega t. So we are going to consider this. Okay, we are going to consider the solution exactly like this. Where psi of r is the amplitude and e power minus I omega t is the phase factor. So we have taken this one, phase factor. And of course, yesterday we discussed about linear operators. As I said, the linear differential equation solutions all will be linear. So obtained operators also will be linear. So all dynamical variables which are associated with the observables. Observables are operators. All observables are associated with the operators. Okay, any dynamical variable which should depend on x comma p are dynamical variables. Okay, so all the transformation in quantum mechanics are linear. Okay, so now we have assumed this solution. Okay, psi of r comma t equal to psi of r e power minus I omega t. So omega is the angular frequency and e power minus I omega t is a phase factor, where psi of r is the amplitude of the wave. And omega is angular frequency and nu is the linear frequency. So omega equal to 2 pi nu. So now differentiate with respect to t. We just differentiate this equation with respect to t. Okay, only once we will differentiate twice, and we are going to substitute in this equation. Okay, we are going to differentiate this one with respect to t and substitute. Let us see how it goes. So differentiating this equation will give you only once. So psi of r is constant. Now we are going to differentiate with respect to t, correct? So psi of r is constant. So when you are going to differentiate, this will give you minus I omega e power minus I omega t. Again you have just to differentiate. So psi of r is there, minus I omega is there. You are going to differentiate once, that will give you minus I omega e power minus I omega t. Minus minus plus. I into I squared minus 1, so minus. Your omega into omega square. Your psi of, combining these two, psi of r e power minus I omega t will give you psi of r comma t. Correct? Is it okay? You will have psi of r and e power minus I omega t. Already psi of r e power minus omega t is nothing but psi of r comma t. So minus omega square psi of r comma t. So now substitute in this equation. So we have this equation 1.27. You substitute, you will have del squared psi of r comma t equal to minus omega squared. B squared is there. So b squared psi of r comma t. Equation 1.30. Any doubt in this equation? So since omega equal to 2 pi nu, we know already the angular frequency and the linear frequency is related with this expression omega equal to 2 pi nu and v equals nu lambda. Okay, you substitute in this equation. Minus omega squared by v squared. So you will get omega squared, correct? Omega squared equal to 4 pi squared v squared, correct? Omega squared equal to 4 pi squared nu squared, and divided by, we have v squared is there, correct? V squared will be nu squared lambda squared. So nu squared lambda squared, this one will go off. Is it okay? So you will have 4 pi squared divided by lambda squared. And of course from de Broglie hypothesis, lambda equal to h by. So lambda squared will be h squared by v squared. You substitute here. So you will have minus 4 pi squared instead of lambda squared, h squared by p squared. So p squared will go to the numerator. So p squared psi of r comma t. And of course we know p equals mv. So p squared is replaced with m squared v squared. So we will keep this equation 1.33 as such. Any doubt in equation 1.33? Very simple equation. Now as I said already that Schrödinger took two concepts. One is de Broglie hypothesis, another one is conservation of energy. So this is your conservation of energy. Okay, total energy equals kinetic energy plus potential energy, and in fact kinetic energy equal to total energy minus potential energy. So kinetic energy, expression for kinetic energy equal to half mv square, which is equal to E minus V. You just multiply up and down with m. So that will give you m squared v squared. You bring these two terms that side. Okay. Why? Because we have m squared v squared is there. So we are going to replace with m squared v squared with this. So that's the idea. Is it okay? Multiply, divide by m. Multiply, divide by m. Okay. So you have m squared. And that 2m will go this side. So 2m E minus V, that's all. So you have minus 8 pi squared. These two, and previously you have 4 is there, correct? 4 is there. So substitute here. So minus 8 pi squared by h squared m into E minus V. Is it okay? This equation 1.36. Okay. Now you just bring the potential energy term to this side. So this is potential energy. So potential energy to this side, that will give you 8 pi squared, m is there, you have V is there, psi of r comma t, minus becomes plus. So you have total energy is that side. So kinetic energy plus potential energy will give you total energy. See, look at this expression, it has changed in terms of h squared, E, m and all those things. Now multiplying this equation by h squared by 8 pi squared m. You multiply this equation. Okay, this equation h squared divided by 8 pi squared m. Is it okay? Yeah. So you will have h squared divided by 8 pi squared m del squared psi of r comma t. This one will get cancelled, correct? This term will get cancelled. This term also will get cancelled. So you have this term 1.38 equation. So minus h squared divided by 8 pi squared m del squared psi of r comma t, V psi of r comma t and E psi of r. So this is the expression for your kinetic energy. This is the expression for potential energy, and this is the expression for total energy. Okay. Now we know already h squared divided by 8 pi squared, that can be replaced with the reduced Planck constant. Yesterday we looked into reduced Planck constant, h bar equal to h divided by 2 pi. So you have h bar squared equal to h squared divided by 4 pi squared. So we can replace h in terms of h bar squared. So this can be replaced by h bar squared. Okay, 1 2 is left out. Okay, we have taken 1 2 out. So 2 into 4. So 4 pi squared. Instead of 4 pi squared, we can write this one. So minus h bar squared divided by 2m del squared psi of r comma t plus V psi of r comma t equal to E square. So this is the conservation of energy. So kinetic energy plus potential energy equal to total energy. So this solution psi depends on r comma t in this equation. So this equation is known as Schrödinger time dependent equation, because solution depends on both r and t, position coordinate and time coordinate. So this is a time dependent Schrödinger equation. Okay, or either sometimes we will call this as energy eigenvalue equation. So is it okay? Time dependent Schrödinger equation. So very important. So out of this time dependent Schrödinger equation and time independent Schrödinger equation, we can solve many problems. Most probably, so first as I said, psi can be known. If psi is known, the complete information about the quantum particle is known. So psi should be known. If psi is known, E can be also calculated. Energy can be calculated. So if energy is known, of course we can find out color, lambda, velocity, radius, all those things will be calculated. So E is very important. And another thing is probability density also can be calculated. Probability density is nothing but psi star psi. If psi is known, psi star psi, that will give you probability density. So all the information can be obtained if you know this equation. So this equation is the pillar in quantum mechanics. So it's a base in quantum mechanics. In addition to that, we can solve many models. For example, quantum well problem, barrier problem, penetration problem. For all the problems we can use Schrödinger time independent equation. So they are all bound states. We will have discrete energies. But when you go for time dependent equation, that is time independent equation. Okay, previously I said this is time dependent equation. This equation can be used to find out the energy for the continuous scattering problem. So in time dependent perturbation problem. So we'll be using all those things. Okay. So now we'll check whether this first term is kinetic energy, expression is kinetic energy or not. We are going to check. So kinetic energy equal to half m square. We know already. We are going to check. Of course, this is potential energy. V alone is there. This is total energy. E alone is there. And we do not know about this expression. Okay. So whether this is really kinetic energy or not, we'll check. So kinetic energy equal to half m squared, we know already. Multiply and divide by